NASA's newest space observatory allows researchers to see further into the cosmos than ever before.
The first reaction wasn't excitement, it was disbelief. When the James Webb Space Telescope finished scanning a distant, supermassive black hole, the raw data didn't look dramatic. There was no explosion, no sudden spike off the charts, just numbers, timing sequences, radiation signatures. But within minutes of plotting the curves against existing models, something didn't line up. The geometry was wrong. Light was arriving from an angle it shouldn't have been able to take. If the models were correct, that region of space should have been hidden, sealed off by gravity itself. And that's when they started moving, not away from the data, toward it. Phones out, simulations running, archived observations pulled for comparison. Because when light behaves in a way that contradicts the structure of space-time near a black hole, you don't ignore it, you test everything. Black holes are supposed to trap light forever, but what Webb recorded suggested that something near the event horizon wasn't behaving like a perfect trap. It was behaving like a warped mirror, and that changes the story entirely. To understand why that's such a big deal, we need to rewind. Black holes form when massive stars collapse under their own gravity. When nuclear fusion can no longer push outward, gravity wins. If the star is heavy enough, nothing stops the collapse. Not radiation, not atomic pressure, not even space-time itself. The result is a region where gravity becomes so intense that escape velocity exceeds the speed of light. That boundary is called the event horizon. The event horizon isn't a wall, it's not a surface you can touch. It's a limit in space-time. Cross it, and every possible future path leads inward. For decades, this was treated as absolute. Whatever happens beyond that boundary cannot influence the outside universe. Invisible, disconnected, final. So when Webb's data showed radiation appearing from a region that should have been hidden behind the black hole, the only possibilities were the instruments were wrong, the model was incomplete, or space-time near the event horizon behaves differently than we thought. The James Webb Space Telescope observes primarily in infrared light. That allows it to peer through dense gas and dust in active galactic centers, the regions where supermassive black holes consume matter. When matter spirals inward, it forms what's known as an accretion disk, a rapidly rotating disk of superheated gas. Above that disk forms the corona, an extremely hot region that emits intense X-rays and high-energy radiation. These environments are violent. Gas moves at relativistic speeds. Magnetic fields twist and snap. Temperatures reach millions of degrees. Variability is expected. Chaos is expected. But what Webb recorded wasn't simple chaos. The radiation pattern showed a flare, followed by a structured delay. The delay wasn't random noise. It had a geometry, a timing signature, a curved path consistent with extreme gravitational bending. And that's when the simulations began running. Einstein predicted something extraordinary in 1915. Mass bends spacetime. Light follows curved spacetime. This effect, called gravitational lensing, allows massive objects to distort light from behind them. We've seen galaxies stretched into arcs because of it, but near a black hole, lensing becomes extreme. Light can loop around the black hole, orbit it briefly, even emerge from behind it after taking a curved path through warped spacetime. That appears to be what Webb captured. Not light escaping from inside the black hole, but light from material behind it, bent so severely by gravity that it curved back into view. That alone confirms Einstein, again, under extreme conditions. But something else stood out. The reflection pattern suggested interaction extremely close to the event horizon, closer than most instruments have ever resolved. This is where things get interesting. Black holes sit at the intersection of two great theories: general relativity, which describes gravity and large-scale structure, and quantum mechanics, which governs the smallest scales of reality. Both theories work remarkably well, but when pushed to extremes, like the center of a black hole, they conflict. At the core of a black hole lies what equations describe as a singularity, a point of infinite density. Infinity in physics is not a solution. It's a warning. It tells us the theory has reached its limit. And then there's the information paradox. Quantum mechanics insists that information cannot be destroyed, yet black holes appear to erase everything that falls in. This contradiction has troubled physicists for decades. Webb's data doesn't solve the paradox, but it sharpens the boundary where that paradox lives. The behavior of radiation near the event horizon suggests that this boundary may not be as simple as once thought. Some theoretical models, including the holographic principle, propose that information about what falls into a black hole may be encoded on its surface. Instead of being destroyed inside, it could be stored in subtle quantum states along the event horizon. If that's true, the boundary isn't passive, it's active, dynamic, a place where gravity and quantum effects interact. Webb can't measure quantum information directly, but it can reveal how energy behaves in that extreme gravitational environment. Every reflection, every delay, every warped echo. It helps refine our understanding of that edge. Then there's rotation. Most supermassive black holes spin, and when a black hole spins, space-time itself is dragged around it, an effect known as frame dragging. In rotating black holes, described by the Kerr solution to Einstein's equations, the geometry becomes even more complex. Light paths twist, orbits distort. The echoes Webb detected are consistent with a rapidly spinning black hole, which means we're not just observing mass, we're observing warped space-time in motion. That allows scientists to measure spin rate, mass distribution, accretion disk geometry, all from how light bends and returns. And that's why they started running simulations immediately, because these reflections are like fingerprints. They tell us how space-time is shaped at the very edge of the abyss. There was no panic in the control room, but there was urgency, because whenever theory meets precision observation this closely, every detail matters. Webb didn't break Einstein, it confirmed him, again, under some of the most extreme gravitational conditions ever measured. But confirmation doesn't end inquiry, it deepens it. The closer we observe to the event horizon, the more we realize it's not a simple dividing line between existence and oblivion. It's a region of structure, of interaction, of complexity, and that complexity hints at something larger. Black holes were once described as cosmic endpoints, places where physics stops. Now they're becoming laboratories, testing grounds for quantum gravity, extreme environments where the nature of space-time itself is exposed. Webb didn't reveal what's inside a black hole, but it revealed something equally important. The edge is alive with structure, and that structure forces us to rethink how absolute the event horizon really is. Minutes after NASA scientists saw the geometry of those delayed signals, they weren't running from danger, they were running toward deeper questions. Because when light takes a path it shouldn't be able to take, when the edge of space-time behaves like a warped mirror instead of a silent void, you don't rewrite physics overnight, you refine it, you test it, you push it further. And Webb just gave us the sharpest view yet of the boundary between what we understand and what we're only beginning to.